All right, so welcome back, everyone. If we could take our seats, we're going to get started with the second half of the Discovery Education 3M Young Scientist Challenge for 2014. Having a good time so far? Well, let's bring out our next finalist. Christopher, are you there? So let's welcome Christopher Isozaki, everyone. Christopher, this is for you, my friend. Are you ready to go?
Yes, very excited.
Saw Christopher on TV this morning, first thing. Did a great job. We've had, just a great week, so knock him dead.
Thank you.
Round of applause, everyone.
We are consuming too much electricity, and if we do not reduce our consumption, we will continue to harm our environment, have risk of having to use riskier energy solutions, and have a harder time acquiring non-renewable resources. My goal was to reduce the amount of electricity used by a computer by creating a new cooling system. This project has been an evolutionary process with many prototypes along the way. I first studied standard and existing cooling systems. The most common system consists of heat sinks and fans, and a cooling system used by a small percentage of computers is liquid cooling. However, both cooling systems are heavily reliant on using a significant amount of electricity. I found that the two main physics principles used in order to transfer the heat off of the CPU are conduction and convection. Air is a very poor conductor, and water is significantly better. However, certain thermal compounds are even more efficient. I did not know about heat pipe technology when I was designing my first prototypes, so I decided to look at other technologies to build them. I decided to use aluminum because it is relatively inexpensive, fairly easy to work with, and a good conductor. I used heat sinks in my first working versions because they increase the surface area in contact with the air, allowing it to convect more efficiently. I was aware of thermoelectric technology, and I thought that this would be a good application for them. Using the waste heat off of the CPU, I create the hot side for the thermoelectric generator, and by dissipating the heat on the opposite end, I create the cold side, which creates a differential in temperature, which enables me to create an electric current. I then use that electricity to power a thermoelectric cooler, which creates a hot surface and a cold surface. I use that cold surface to help cool the computer. Using these principles and ideas, I was able to design my first working prototype. It was successfully able to reduce the amount of electricity a computer used by about 32%. However, it had many issues. First, there was risk to damaging the computer parts due to water damage because it contained water on the inside, and there was condensation around the thermoelectric cooler because it creates a cold surface surrounded by hot air. Also, it was quite large, making it difficult to implement into many computers, and it was quite ugly. In order to solve these issues, I looked into ways to try to resolve them. I found heat pipe technology in my research and thought it would be a good way to not only transfer the heat more quickly, but also to increase my surface area rapidly. On the hot end, the heat pipes vaporize a fluid. And then, because of the increase in pressure, the fluid is forced to the opposite end of the heat pipe. And then, by releasing the heat outside of the system, the molecules slow down and condense, like so. Sorry about that. Then, using capillary action, the fluid is able to move back onto the hot end, so that way the system can continue. Capillary action is demonstrated in how the fluid rises up these paper towels. Next, I looked into a way to create a separate compartment in order to cool the cooling system outside of the main, away from the CPU, also to remove the risk of condensation damaging the computer parts. I added an insulating wall using 3M heat foam, which enabled me to prevent the heat from traveling back into the main compartment. Next, I looked into ways to maximize the contact between the materials. When two flat surfaces are together, they look like they have good contact. But if you look closely, where the light passes through, there are gaps where air is. This causes it to conduct poorly. Using these new ideas, I was able to create several new prototypes. My latest version not only can better cool the cooling system, but it addresses all the issues I had addressed for my first working system. It also has a thinner profile, enabling it to be used in a wider variety of computer systems. Because my cooling system is able to reduce the amount of electricity used by about 32%, if it were implemented in half the current cooling systems computers around the world, it would reduce the oil consumption by about 8 billion gallons a year and reduce CO2 emissions by about 310 billion pounds each year. Thank you to 3M and Discovery Education and all other people who have supported this contest. It's really been an experience of a lifetime for me. I would like to help keep our environment beautiful. Thank you.
Christopher, thanks for a real cool innovation. Have you taken the time to estimate roughly what the cost of this type of cooling device might be relative to the amount of energy savings that it would provide?
Yes, I actually have done some research and have called some certain manufacturers, and they told me if it were mass-produced, I would be able to create this new cooling system for roughly about $35 for sales, to sell it at a profit. They told me that it would cost about $25 to make. The reason that it would pay for itself, because even though it is more expensive than current cooling systems, it can pay for itself because every time you turn on your computer, money's flying out the window because you have to pay for the electricity. This would reduce your energy bill that goes towards your computer system by about 32%.
Christopher, if you had to do this over, what would you do differently?
If I could do this over, I would like to look into existing technologies more extensively earlier. As I told you in my first videos, in my first prototypes, I did not know about heat pipe technology. It greatly improved my design, but I had to use aluminum because I was unaware of this technology. I was also unaware of all the types of cooling systems, and some of them gave me certain ideas that I was able to implement into my idea. Also, I was able to remove the heat pipes because I learned more extensively about the science behind how I'm convecting the heat off of my innovation.
Pretty cool innovation, Chris. It is a worldwide issue again. Did you quantify the delta H in terms of existing computers versus your version? What type of heat exchange? Did you quantify it in any way, calculations?
What I did was when I performed my testing, I was able to produce results with the control of just using multiple computers, almost identical to this one, same model, and they used a certain amount of wattage. It was about between 140 something watts, I'm sorry, I don't know the exact number, and about 160 watts. This was able to reduce it by about 32%. So if this were in a computer, it would save about 32% of the total energy usage.
What I meant was the actual heat exchange between your version versus status quo computers out there.
The way that mine is more efficient, sorry about that, is it uses heat pipes to conduct it instead of the aluminum. As you saw in my earlier slide that shows information about the conductance, the aluminum was rated significantly lower than were the heat pipes. You'll be able to see it on the board here. Heat pipes are at the top, and you can see how much better a conductor it is. And that's what I'm using to initially get the heat, transfer it off of the CPU, and that's what's keeping the computer cold.
Thank you.
Thank you for your environmental mindset. I appreciate that. How does the complexity of your innovation impact the functionality or efficiency of the computer?
This is able to better cool this computer system because, as I explained, I cool it in a separate compartment that prevents the heat from going back into the main chamber. Also, I'm able to transfer it away more quickly, allowing you to run more demanding programs, use more powerful computers, as well as this saves the energy. The one problem is if you're using a certain chip on the inside, like a high-power graphics processor, I would have to just add another heat pipe to pipe it out into my cooling system because it has no more fans to cool the graphics card. So all I would have to do was add a heat pipe to attach it to my cooling system, and it would work the same.
So Christopher, there are several appliances, devices that their end product may not be and the intention to produce heat, but they do. So why a computer? What experiences have you had around a computer that you decided to take this as the change event that you're working with?
I chose to use the computer because they're all around us, and we're in the computer era, so more and more computers are being produced. So I thought it would be one way that I could implement my system more quickly, because as soon as I could get it ready, people would continue to make computers. Also, I didn't just pick it because it could save energy. Many computers, such as my own, have many failures due to heat because of the mechanical parts such as the fans. Mine uses no moving parts, so the risk of failure is much less. So you would have much less risk of your computer failing due to overheating. Thank you very much.
Nice job. That was
Thank you.
fantastic. Christopher, everyone. Very nice job.